Hello and welcome everyone. My name is Edvard Omdal. I'm the chairman for the chalk and carbonate reservoir network in Force. I want to thank you all for joining in to this first webinar of 2021. Today we are so lucky to have Torben Treffesen from Germany with us to give a presentation called Let's Learn How to Treat Our Faults Better. I got to know Torben last year via LinkedIn, so very typical for this day and age, Corona and all. A little story before, as the numbers are still creeping up with participants. One thing that caught my eye with Torben was that he is making these small, brief YouTube clips explaining geomechanics or geoscience in a nice and clear way. I think that's so nice. You can learn how to do most things today from fixing your car or making food or fixing a house or everything. So why not also geomechanics and geoscience? And so I really encourage that. But also Torben, he has been doing his undergraduate work at the University of Darmstadt in Germany. And in his master thesis work, what he did was to compare how we represent faults in different software packages. And what do you know, he kind of discovered that there are better ways or still things that we should learn. And one of them is how to represent faults better. And this interest is what gave him the PhD position, as I understand it, and his PhD was what he is going to present for us today, and he finished that late 2020. So Torben also has other interests. I want to mention that he is part of a federal commission in Germany, linked to the Christian Democratic Union, which is the government party in Germany. So they have, so he is spending his talent on the climate and environment and energy, is how to use science in order to use our planet in a more sustainable way. And if the presentation today doesn't go the way you want it, Torben, I hear that Angela Merkel is looking for a replacement these days. So I think you should be okay anyway. You have a bright future. So, but on a more serious note, I know that Torben also have not too many weeks left at his employment at the university, and who knows? Perhaps there are some in the audience that are familiar with the reservoir that you use as an example for your model. I think that's a reservoir from the Norwegian continental shelf, and we always wish you welcome up here in Norway, as we do with all the German tourists in the summer. So so I think you'll like it here as well. So with that introduction, I hope that we have reached a stable amount of participants, and I'm very happy to see that we are close to 50 people. So with that, take it away, Torben.
Thank you, Edward, for the kind introduction and the opportunity to hold this webinar. Let's learn to treat our faults better. It's really a pleasure to be here and discuss with you what could be the future of fault representation. Let me start with giving you a short outline about what I will cover in this webinar. Basically, it will be divided into 3 parts. The first part will start with background information to get us all on the same page. I will talk about why faults are important in reservoir simulations, what challenge we face while incorporating faults, and how faults are treated in finite element models today. The second part, I will present my PhD entitled Fault Representation in Reservoir Scale Hydromechanical Finite Element Models, and talk about whether there are differences in the results derived from different fault modeling approaches. The goal is to give you some hands-on recommendations you can directly use to treat your faults better today. The first Third and final part will focus on what I think can be the future of fault representation. I will introduce two possible further developments which I believe could really improve fault representation in reservoir models in the future. I will present two Python prototypes and somewhat outline the path ahead to implement those techniques in the industry workflow. All right, now let's start with talking about the motivation behind this work. And here you can see the structural model of a reservoir as an example. This is the GoFX reservoir model, which is based on the interpretation of 3D seismic and well data, and thus represents a real-world example. As you can see, it contains plenty of faults, penetrating and offsetting the reservoir horizon. Why are faults so important? Well, first of all, they have a profound control on the hydraulic regime, as they can act as conduits or barriers for fluid flow. From the mechanical point of view, faults affect the regional stress field, which results in local changes in stress orientation and magnitude. Considering the usually weaker mechanical properties of fault zones if compared to the undeformed host rock, they are more sensitive to pore pressure changes resulting from fluid injection into or fluid withdrawal from the reservoir. In the worst case scenario, these pore pressure changes can reactivate pre-existing faults, leading to induced seismicity, which in turn potentially causes real critical situations like fault seal breach, land subsidence, and well collapse. Now, before we dive deeper into faults in hydromechanical reservoir models, let's quickly sum up how faults actually look like in nature. Faults are characterized by a complex geometrical structure and a heterogeneous material distribution. A fault zone typically contains at least one fault core accompanied by damage zones on either side. Structurally more complex faults include multiple fault cores as well as damage zones of variable width and fracture intensity. Because of this internal complexity, a fault should be regarded rather as a fault zone and a volumetric feature than as a discrete fault plane. This structural complexity and heterogeneity of the fault zone varies on a scale of centimeters to meters. So the first challenge for an appropriate representation of faults in numerical reservoir models is the difference of the geometrical complexity as well as internal scale of the fault zone, centimeters to meters, and a typical cell size, meters to tens of meters, of a numerical reservoir model. All right, now let's go back to the GoFX model. I'll show you the wall locations drilled during the development of the GoFX reservoir. And as you can see, none of them crosses the fault zones, because faults are usually not a target for drilling operations. In fact, we normally try to avoid fault zones during reservoir development to reduce well stability problems. And even if coring of the fault zone is attempted in order to receive samples for testing, intense fracturing and poor consolidation of fault zone rocks frequently lead to very limited core recovery. As a consequence, there is usually a lack of fault-specific material parameters to populate a hydromechanical model. Instead, the material parameters often have to be estimated from literature sources. So the second challenge is the lack of fault-specific material parameters regarding fault zone properties. Before we go on to my PhD, let me quickly explain the three main approaches used to implement faults in reservoir scale finite element models. Numerically, we can divide them into a discontinuum description, which are contact elements in this case, and a continuum description, which is a volumetric weak zone. Let's begin with the discontinuum approach. Contact and the corresponding target elements are defined at opposing sides of the pre-signed faults. So contact elements do allow differential movement between individually meshed parts of the model. A downside of this approach is that the fault is not represented as a volumetric feature, but by a line in 2D and the surface in 3D models, respectively. All right, now let's see what the continuum approach looks like. The concept of volumetric weak zones describe faults in a finite element model by assigning usually weaker fault rock material properties to the grid cells intersected by faults. To do so, a frequently used approach is to implement a volumetric fault zone into a rectangular grid by intersecting this grid with a structural model and assigning fault rock properties to those cells cut by the fault planes. Such a rectangular grid is fast and easy to generate and therefore saves time in model generation. Another approach to incorporate faults in reservoir models is to adapt the grid to the fault zone geometry. This allows a representation of the fault which is closer to reality, but adjusting the grid to the fault geometry takes significantly more time to generate, especially for large reservoir models including multiple fault zones. All right, I will start presenting my PhD by showing you what we imagine to be the possible decisions a modeler faces during fault representation in hydromechanical reservoir simulations. We wanted to investigate the qualitative influence the different approaches as well as numerical assumptions and simplifications by the modeler have on the modeling results. First, we differ between this continuum description, which are contact elements in this case, and the continuum description, which is a volumetric weak zone. Second, two different grid geometries for the continuum approach were investigated. A curvilinear grid with the model grid adapting to the fault shape, and a rectangular grid with fault rock properties assigned to the cells cut by fault planes. Also, the mesh resolution inside the fault zone is investigated further. Lastly, input values like the fault dip and the elastic and frictional properties and their influence on the simulation results are reviewed. We started with a simple mechanical 2D plane stress model. The fault zone is included by using different approaches. The continuum approach with both rectangular and curvilinear grid, and a discontinuum approach with contact elements. The model describes the top view on a vertical strike slip fault. And these are the elastic and frictional properties used in the study for the host rock and the fault zone. Please note that the contact algorithm only takes cohesion and friction angle into account. The failure criterion used is Moore Coulomb with a tensile cutoff. Now, this two-plane stress model was our first approach to mainly investigate contact elements versus volumetric weak zones. In this presentation, I will limit myself to reviewing the stress magnitude pattern from the maximum principal stress S1 derived from the simulations. From left to right, the results achieved with the rectangular, curvilinear, and contact approach are displayed. Clearly, the most pronounced effect regarding spatial extent and changes in stress magnitude is observed for fault representation as volumetric weak zone with a continuous curvilinear grid adapted to the fault geometry. A somewhat intermediate effect was found for the fault representation via contact elements. A fault representation as rectangular grid has the least impact. These observations are the same if stress orientation as well as strain magnitudes are considered. One last point. I'm sure everyone is asking themselves, why are there differences between the rectangular and the curvilinear approach if both use the same numerical approach, volumetric weak zones? I will tackle this question soon when I present the results for the other research articles where mesh resolution and grid geometry for the volumetric weak zone approach were of special focus. We have seen the different fault representations as contact elements or volumetric weak zones produce. Since a volumetric representation enables a 3D representation and thereby incorporation of internal heterogeneity of a fault zone, We focus on this in the following research. To investigate volumetric weak zones and their different simplifications, I imagined an elliptic fault zone displacing a reservoir horizon as geological rationale for this model setup. The actual model represents a one-element wide slice through the central part of this fault. This generic finite element model with a volumetric fault zone description has very simple boundary conditions. Gravitational loading, including a lithostatic pressure boundary condition at the top, and a hydrostatic pore pressure field defines the initial state. The fully coupled hydromechanical simulation is run over a period of 5 years, while increasing the injection pressure in the reservoir of the downthrown block by 3 megapascal per year. Now, let me show you the material properties used in this study. They are the same for all rock units in all scenarios, for comparing the mesh resolution, grid geometry, and fault dip. We also investigated what influence different material properties inside the fault zone have on the simulation results. In this sensitivity study, 87 finite element models with different mechanical parameter combinations assigned to the curvilinear fault zone have been studied. We varied Young's modulus, Poisson ratio, cohesion, and angle of internal friction within a range typical for fault zone rocks and siliciclastic suggestions to examine what effects such upscale parameters have on the simulations. All right, since we have discussed the modeling setup, I want to show you a short animation of the simulation results for the curvilinear approach. You can observe how pore pressure, maximum effective stress S1, and plastic strain change over time. Injection leads to an increase in pore pressure, and this increase in turn affects the stress field, not only in the vicinity of the fault. Inside the fault zone, the pore pressure increase reduces the effective stress, and the plastic strain spreads out from the fault tips until the whole fault zone is reactivated and shear deformation occurs along the whole fault zone. After we have seen how the simulations and results look like in general, let's move on to investigate what influence mesh resolution inside the fault zone has on the simulation results. Here we can see the results for the plastic strain if the fault is represented either as a 1, 3, or 9 element wide zone in a rectangular grid. Clearly, significant differences occur between 1 element case on one side and the 3 and 9 element cases on the other. Obviously, there's no plastic strain for the 1 element row representation at all, so the fault is not reactivated here. While between the 3 and 9 element wide fault zone scenarios, modeling results are rather similar. Plastic strain is spread out over the whole fault zone for the 3 and 9 element wide fault zone. Now, let's switch to the results for different grid geometries, the rectangular and curvilinear grid, by looking again at the results for the plastic strain. The rectangular approach is displayed in the top, and the curvilinear approach in the bottom row. If we consider the overall strain pattern, we're here both the rectangular and curvilinear approach look quite the same. But if we take a closer look at the fault tips, we see that the trend is different. While the plastic strain for curvilinear approach increases towards the fault tips, as we would expect from observation in nature, the rectangular reverses this behavior and decreases towards the fault tips. Let's move on to the actual fault zone properties a modeler has to define during a reservoir simulation, and start with the results achieved for different fault tips. The fault tip is 60 degrees in the top and 90 degrees in the bottom row, and both faults are 3 element wide curvilinear fault zones. The results displayed here from left to right are pore pressure, magnitude of S1 effective, and plastic strain. Obviously, a large difference can be observed for both S1 effective and plastic strain. In fact, there's no plastic strain and therefore fault reactivation in the model with a 90-degree fault tip at all. However, the hydraulic part of the simulation doesn't seem to be affected at all, and the pore pressure increase affects the upper reservoir compartment in both simulations. Now, what is the influence of varying elastic material properties inside the fault zone on the simulation results? Here, the Young's modulus of the fault zone decreases in the models from left to right from 10 gigapascal to 0.1 gigapascal. We can see the results for the magnitude as well as the orientation, or more precisely, the rotation away from the original vertical direction of S1 effective. It's clear that both parameters increase in both actual value and extend around the fault zone with decreasing Young's modulus and hence increasing stiffness contrast between fault zone and surrounding rock. The second elastic property we investigate is Poisson ratio. The results for S1 effective and S2 effective are displayed here. Again, the Poisson ratio inside the fault zone decreases from left to right from 0.25 to 0.1. Please note that the Poisson ratio in the surrounding rock mass is kept the same in all scenarios. Examining the results, we can hardly detect any differences between the modeling results. After we have considered the elastic material properties, we now examine the frictional material properties of the fault zone and start with cohesion. Here we have displayed the results for elastic and plastic strain. Cohesion of the fault zone rocks decreased from left to right from 5 megapascal to 0.01 megapascal. And it's striking that the results with a cohesion of 5 megapascal are different than the other two, which are quite similar. We finish presentation of the modeling work by comparing the results achieved with different friction angles. The internal friction angle of the fault zone is 25 degrees, 17.5 and 10 degrees. And the results displayed here are again the magnitude and the orientation of S1 effective. At first, the results appear to be quite similar, but if you take a closer look, especially at the fault tips, we see both parameters increase with decreasing friction angles in a more or less linear way. Now, let's sum it all up and integrate the results of my PhD into the decision tree a modeler may face during fault incorporation in reservoir scale hydromechanical models. Regarding the numerical approach, contact elements or volumetric weak zones, results of this thesis indicate that the smaller the scale difference between the general element size of the model and fault zone, the more worthwhile is the representation as a volumetric weak zone. On a reservoir scale, such a volumetric representation as a weak zone enables incorporation of more details, starting with simply subdividing the fault zone into fault core and damage zone. In contrast, in models tending towards the regional scale, contact elements may be the better choice due to the huge scale difference between the fault zone and the elements of the finite element model. Looking at both grid geometries, for a volumetric weak zone, similar stress and strain patterns are obtained at a distance of more than 10 meters away from the fault zone, and hence both are interchangeable here. Based on this consideration, the modeler may choose a rectangular fault representation when modeling a full-scale reservoir, and only using the curvilinear representation where a fault zone is of special interest. Adapting the grid to the fault zone and using a curvilinear fault zone representation requires much more time in model generation, and therefore may only be reasonable if the aim of the study is inside or in the vicinity of the fault zone. The mesh resolution has to be considered very carefully, since it can, combined with a rectangular grid, lead to serious errors. It needs to be ensured that the fault sets do not interlock with the surrounding, stronger and less permeable host rock, as this affects both fluid flow through and straining of the fault zone. This interlocking effect mainly occurs for one element-wide fault zones. For grids with multiple element-wide fault zones, the only differences are observed in the vicinity of the fault tips. 3 element-wide fault zones appear to be appropriate for most reservoir scale models. Only if the aim of the study is within a few tens of meters of the fault zone, a finer grid resolution should be considered. Different fault tips produce results in different stress and strain patterns. Therefore, care should be taken to consider a realistic fault tip, rather than using a vertical fault tip for simplification. But different fault tips produce similar hydraulic results. So if the aim of the study is primarily on hydraulic issues, vertical faults can be an acceptable simplification. Speaking about the material properties assigned to a volumetric weak zone, no significant impact on the stress and strain pattern in the far field of the fault is observed. Far field in this respect means at distances of more than a few hundred meters to the fault. So if your modeling project doesn't focus on the vicinity of a fault, the fault zone properties can be determined based on literature data and a rule of thumb. In contrast, if near field zone is of interest for the particular modeling project, care should be taken to find appropriate values for Young's modulus and cohesion. The angle of internal friction is of less relevance, and for the Poisson ratio, the standard value of 0.25 can be adopted without concern. I hope these recommendations following the results of my PhD will help you to treat your faults better today. However, there are still open questions and research areas for fault representation in finite element models. So, what's the future of fault representation? Well, basically I would divide future developments into more detailed fault zone models and new upscaling techniques, especially for hydromechanical or even hydrothermomechanical fault zone material properties. Don't get me wrong, this is not fully scientifically verified. These are some ideas which came up in my mind, thinking about what I've learned about fault representation in the past 3 years, and what needs to be done to improve it further. I already developed Python prototypes to tackle these issues. Of course, these prototypes need further development, testing, verification before they can be implemented into the industry workflow. However, I truly believe this can be the future of fault representation. Let's start by talking about a detailed fault zone model. As we know, fault zones in reality are more complex than how we represent them in reservoir scale models. So we should investigate what the results for a more detailed fault zone model would look like, especially what differences can be observed on the different scales. Now, how could such a more detailed fault zone model look like? Well, the fault core could include fault core lenses embedded into a highly deformed fault core material. The damage zone could be divided by the origin of its material, but also into zones to honor the decreasing fracture density with increasing distance to the fault core. All right, let's have a look at a short animation of such a detailed fault zone model. This is the case for a permeable fault zone, and the overview of the model domain is displayed in the top row. The bottom row shows a model section 50 meters around the midpoint of the fault. You can observe how pore pressure, maximum effective stress S1, and plastic strain change over time. Overall, the injection leads to an increase in pore pressure, and this increase in turn affects the stress field, not only in the vicinity of the fault. Also, the plastic strain spreads out from the fault tips until the whole fault zone is reactivated. Looking at the inside of the fault zone, we can clearly detect the fault core lenses with their stronger mechanical properties, as well as their smaller permeability than the surrounding fault core material. The fault core lenses show no plastic strain, and all the deformation occurs in the surrounding fault core material. Another case we investigate right now is a detailed impermeable fault zone. Again, the overview of the model domain is displayed in the top, and the bottom row shows a model section 50 meters around the midpoint of the fault. Most of the results look quite similar to the ones we saw for a permeable fault zone. The injection leads to an increase in pore pressure, but almost stops at the impermeable fault zone. So the effect of the effective stress is also more or less limited to the right side of the fault zone. If you look at the plastic strain, we see that it again spreads out from the fault tips until the whole fault zone is reactivated. However, I think it's really interesting that first, increasing plastic strain occurs around the fault core lenses opposite to the pore pressure increase. It takes a long time until the right row of fault core lenses starts to exhibit plastic strain. But then the increase is much faster until the most plastic strain is accumulated at the right side of the fault core. Interesting results, aren't they? Now, you may say implementation of detailed fault zones in reservoir scale models would take too much time to generate. But what if we can automate detailed fault generation? And yes, we can do that. I've already written a Python application called FaultGeometry with a graphical user interface where you can define various input values for the fault geometry. FaultGeometry can then create an input file including all commands needed to generate the model geometry. All that needs to be done in ANSYS is meshing of the predefined volumes and assigning reasonable material properties. This script reduces the time needed to create such a complex fault geometry from days to seconds. The whole model setup, including material properties and boundary conditions, can be done in less than 30 minutes. Now, why do I believe that FaultGeometry can be a prototype for future fault representation? Imagine this. Instead of returning ANSYS commands to generate a detailed fault zone model, a plugin is fully integrated in the software you use. While you build a model geometry, you have to somehow define the fault zone. And here you have the option to simply define those inputs FaultGeometry uses. Afterwards, the fault zone geometry is automatically implemented into the reservoir model, also taking intersections with different layers into account. In a second step, the material properties of the fault zone rock units can be defined, completing the integration process for the detailed fault zone. Now, what needs to be done to integrate FaultGeometry in a reservoir simulator? First, it has to be upgraded because right now FaultGeometry more or less creates a 2D fault zone model. However, I don't think this would be a big issue. From a software engineering point of view, enhancing the used 2D formulas to 3D shouldn't be that much of a challenge. And from the geological point of view, all the scaling laws I used, for example, for the lens dimensions, exist in 3D too. So I think upgrading this tool from 2 to 3D is a delicate but routine piece of work. Second, the code has to be converted into the programming language the desired reservoir simulator uses. There's one challenge left for integrating more detailed fault zones and reservoir scale models: the model size, or more precisely, the number of elements needed. Ain't they increased significantly for such a detailed fault representation? Well, of course they do, but our industry is improving computation capabilities rapidly. I know that two big companies are working on pushing the boundary for reservoir simulations beyond 1 billion elements right now. And that will enable us to include such small-scale variations into reservoir scale models. Now, let's switch to the other option I suggested for future developments: a new upscaling workflow, especially for hydromechanical or even hydrothermomechanical Poisson material properties. Now I know we have pretty good empirical formulas for upscaling hydraulic properties. In contrast, no formulas for upscaling the mechanical properties exist, which is mainly caused by their nonlinear behavior. The basic idea behind this new workflow is to enable a concurrent upscaling of hydraulic and mechanical material behavior by focusing on the desired results and not on the actual material properties. Let's jump right into it to give you a better idea of what I mean with that. The workflow starts with a regional reservoir model, such as the Gulfax reservoir model here. First, one fault zone is extracted, and a detailed model of the fault zone is generated in a relatively generic model setup, similar to the model setup, for example, with FaultGenPy. Using the same generic geology, we set up a database, including a fault zone by only one set of material properties. This database is created varying this one set of fault zone material properties through a range possible in the regional setting. Having both the detailed fault zone model and the database allows us using the Python prototype Fault Upscale PI. Now, what does Fault Upscale PI do? Well, first of all, Fault Upscale PI simply plots out the simulation results for the models in the database and the detailed fault zone model using the exact same color scale and saves them as images. Once this image database is generated, the results of the detailed fault zone model are compared with every model using one fault zone element, material. This is done by utilizing the structural similarity index for each image pair, which I'll explain later. Lastly, Fault Upscale PI gives back the one upscaled fault zone material, which matches the results of the detailed fault zone model best. All right, let me show you what the output of Fault Upscale PI look like. In the upper row, we see the results for the detailed fault zone model, and in the second row, the results for the one fault zone material model, which matches the results best. In the last row, the structural similarity index of both images is displayed. Now, what is the structural similarity index? This image processing method computes the exact X and Y coordinate locations where the simulation results are different. Fault Upscale PI calculates a value for the structural similarity index for each pair of results. The value ranges between 0 and 1, with 1 representing perfect similarity of both simulation results. In a last step, fault upscale PI creates a difference image for the result per pair with the highest structural similarity score, which visually shows the x and y coordinates where the differences are. This could help the modeler to decide whether there is a satisfactory fit regarding the aim of the reservoir simulation. You may say, upscaling every fault in a reservoir model with the workflow I suggested would take too much time. But what if we don't need to follow this workflow for every fault? Well, for a sedimentary basin, which we normally have for oil and gas reservoirs, parallel fault zones normally exhibit similar fault behavior. So I would suggest to upscale one fault zone for every set of parallel faults, which limits the upscaling progress significantly. The upscaled fault zone material can then be assigned to all parallel faults in the reservoir. And now I know this workflow needs plenty more testing, but I really believe this somewhat out of the box approach is worthwhile further research. One last thing. You may think the two future developments I suggest are more trouble than they're worth. Why should we try to treat our faults better? First, let's remember faults are zones of usually weaker rock properties compared to the undeformed surrounding rock units. This in turn means that they are more sensitive to pore pressure changes due to production and even more to injection. And faults are normally where stress is released, deformation and induced seismicity occurs in the subsurface. And induced seismicity is a big issue for our industry. Could we prevent something like cloning if we had a better fault zone representation in the models? And what about CCUS? Injection and increasing pore pressure is more likely to reactivate pre-existing faults. So I think faults will be even more important in the future of our industry. I would be happy to connect with you on LinkedIn to share more ideas in the future. Also, LinkedIn is the platform I use to share my latest research. Soon there will be links to GitHub where you can get the source code of all Python prototypes I've introduced. You can also find links on LinkedIn to ResearchGate and the free publications as well as my PhD thesis. So thank you for your attention, and I'm really looking forward to our discussion and hear your opinion on the future of fault representation.
Thank you, Torben. This was amazing. Well, there is a lot of echo now, but well presented and nice and clear. So I guess we'll open up for questions, and for those of you who want to voice your questions yourself, you can do that, or you can put them in the chat, and then I'll voice them for you. I'll start with just a recognition that we as a team of geologists in ConocoPhillips went on a field trip to one of the big tunnel projects in the region, in the Stavanger region, just a couple of years ago, and the entrepreneur had a classification of faults or rocks in general as good rock and bad rock being faults. So I think you've done taken this on a completely different level. So that was good to see. Any questions? So I'll start with the question then. So you've now really shown in detail what the different parameters and gridding and how this works as what's sensitive to movement and behavior, but how, and I guess this is not your work, your side of the work now, but how do we know when what is correct?
Yeah, this is a very good question. Basically, we cannot know what is really correct because to evaluate this question, we should have a fault zone, which is completely where we have all the material properties for all the different fault core units and all the damage zone units. And this doesn't exist in the world. But from a reservoir engineering point of view, we can check our fault by assigning by a calibration process, and therefore see if the results of our faults are fitting for the model we want to see.
Thank you. I see there is a hand. Marcel, do you want to voice a question?
Yes, I would like to do that, and instead of just writing it down in the chat. I referred to the parametric study of the fault parameters that you showed in the beginning of your presentation. And one thing I stumbled a little bit over was that you looked into the effect of Poisson ratio, and I think you started originally at 0.25, and then you reduced that value down to 0.1. And the result was there was basically very little effect on the say stress redistribution between the cases. My question is, why did you reduce the Poisson ratio and did not increase it maybe towards a more plastic or ductile material, say raising it from in the worst case to 0.5 maybe, just to see what is the effect in the opposite direction?
Yeah, this is a good question. We haven't thought about that. I mean, if you want to simulate ductile behavior, for example, I think we need other material laws like the Moore-Coulomb we used. So I think our models are not capable of simulating ductile behavior in the first place. Yeah.
But does this imply that when you said that 0.25 would be the recommendation for you to use as Poisson ratio for fault material, does that hold? Or, I mean, because you said there was no effect, or if you, I mean, if we would believe there is maybe another value to be used higher that, as a matter of fact, would have an effect, but that hasn't been investigated in that study, is that right?
I think there wouldn't be an effect because we saw in our models that there is almost no effect. I think it was I just looked at the values which are directly in the fault zone, and I saw that they are in a behind 2 or 3 values after the comma. So this effect of the Poisson ratio is very little. And the reason for that is because of the surrounding rock material, which has the same Poisson ratio for all the models. So the Poisson ratio of the surrounding rock mass somehow suppresses any effect of the Poisson ratio in the small fault zone. So I think this would also stand for higher Poisson ratios.
Okay, thank you.
I see there is another hand up, Longview. Do you want to?
Sure. Yes, my name is Long from Equinor. So my question, I think previous discussion already answered part of that, but basically 2 things. One is that have you done any calibration and benchmarking, towards the real data? The second question is, have you compared your methodology, this software, with our standard industry finite element tools, for example, Abacus, to verify whether this is numerically similar?
Yeah. Okay, about the calibration process, we didn't do that. because we just want to show the effects each numerical code has, and don't limit that with just calibrating the software. We just want to show what happens if we assign specific material properties. And the other point about the different software types and whether this is a numerical issue. This is a very difficult question. I've tackled that in my master thesis, where I compared ANSYS, Abacus, and Petrel, or the Visage geomechanical simulator of the Petrel software suite, and their approach to simulate faults and the results we get. And the one thing which is really troubling us to really make a good decision on that is the limit that we don't have the code of these simulators, right? They are commercial software, and therefore they are more or less a black box. So we got some results, but we couldn't say where they are coming from and what is the origin in the software code.
Thank you, Torben. There is another question in the chat, and I'll try to read it. So in your opinion, Torben, will the results of stress calculations in the zone of influence of the fault change when considering intersections of the fault? So I guess if other faults are crossing the fault of interest.
Yeah, this is a good question, and I came across that question in other when I present my results at the AAPG last year. I think the results will be influenced by the intersection of faults, of course, since both faults will influence the stress field. But I can't give a opinion on how much this will result. This will result in changing recommendations. I think it won't change our recommendations very much, because we focused on the correct implementation of a fault, and if you implement another fault which crosses or intersects this fault, both faults should be implemented correct on a physical base with the recommendations we did, and the physical simulator you use then would give some correct physical results.
So thank you for that answer. I want to also just give you a comment or maybe an encouragement. What we have, I think within ConocoPhillips, what I think we have experience with is to look for fault activations on 4D seismic.
Mm-hmm.
And then maybe another way to go if you want to calibrate if there is fault activation or movement on the fault could be if you have a closing fault, baffling fault that suddenly starts to communicate. Things like that. Would that be a way to go?
Yeah, I think for the calibration process that would be definitely a good option. From the calibration process, we thought of boreholes in the vicinity of fault zones where we can log the stress orientations and stress magnitudes, as well as for hydraulic parameters, the flow rate, for example. But I think it's also a good thing to calibrate the faults with the seismic, induced seismic.
Thank you. I see a hand, but I'm fearing it's an old hand, I like to call it. But is there another question? No. I think we're gonna let you go then, Tobin. This was great. Exactly what I hoped for. And I'm so impressed that we managed to keep 50 people in at this very specialized topic. So that was great, and I hope I wish you good luck, and I hope that we get to implement some of this knowledge.
Yeah, thank you, Edward, and thank you for having me here. Good day to everyone.
Bye bye.